Hello physical sciences learners, and welcome back to another video with me, Ms. Martins. Today we're going to be looking at past papers that deal with the quantitative aspects of chemical change, and another word for this topic is called stoichiometry. Now you'll see over here that I said that we're going to be doing a grade 11 past paper or multiple grade 11 past papers, questions from those, but if you're in grade 10, this video is going to be for you as well, because in grade 10, you learn about these stoichiometric principles and calculations that you need to be able to apply again in grade 11 and grade 12. This video is for you as well, because in grade 12, the things that you learn in grade 10 and grade 11 will be re-asked in different sections throughout your chemistry exam. So let's go grade 10s, 11s, and 12s. Here's the first question that we'll be tackling. Let's start with 5.1. 5.1 wants us to define the term concentration. This is a very common definition that you'll be asked in grade 10 and in grade 11. And the concentration of a solution is the amount of solute, or the number of moles of solute per unit solution or per unit volume. And it makes sense if we look at our formula. So as we can see, C is equal to N divided by V. It's the amount of solute, N, per unit volume. Per means divide. The definition can also say the amount of solutes per liter solution, something like that. 5.2 actually wants us to calculate the concentration of a solution, but they give us mass in grams. So if you look at that formula that I was just speaking to you about, C is equal to N over V, you'll see that I need the moles. But over here, I'm not giving you moles, I'm giving you grams, which is mass. So one thing that you can do is you can use this formula, number of moles is equal to mass divided by molar mass, to first get the number of moles. Then once we have the number of moles, we can divide it by our volume, which will give us concentration. There's something else that we need to do to the volume before the time though. But let me just show you another way that we can calculate concentration is by using a formula that combines these two formulas together. And basically, if I take number of moles, which is equal to mass divided by molar mass, and I substitute mass divided by molar mass into the place of N in this first formula, I get a second formula that looks like this. And I may use this formula instead. So let's do it. Let's do this question by using this formula. So reading the question, I can see that I have 8 grams of my solute. So my mass is 8 grams. And then they say that it's dissolved in water to prepare 500 cubic centimeters of solution. Now they don't tell me that this is the volume, but by looking at the unit, cubic centimeters, we know that that represents volume. 500 cubic centimeters, but you should know that if you make use of the concentration formula, you need to know that that cubic centimeters needs to be converted to cubic decimeters. And to do that, we divide by 1,000. So if I divide 500 by 1,000, I'm going to get 0.5 cubic decimeters. That is now my volume that I'm going to sub into my formula. So if we take a look at my formula, I'm looking for concentration. So that's my unknown. I have mass. I have volume. I need molar mass. As soon as you know the compound, we can work out the molar mass. Remember, we use our periodic table in order to calculate the molar mass. If you need a recap of this, check out the video in my description down below. But you use your periodic table, you use your atomic mass numbers, which is the big numbers. So sodium, for example, is 23. You multiply 23 by 2 because there's 2 sodium atoms within this compound. Plus, sulfur is 32. We multiply that by 2 because there's 2 sulfur atoms. Oxygen is 16. We multiply it by 3. We work that out. Working that out, we get 158 grams per mole. This compound is called sodium thiosulfate, just by the way. Then we write down our formula, which I've already done. We substitute. So when we substitute, we put our numbers in the place of the variables. MV means molar mass times volume. So we've got 158 multiplied by my volume in cubic decimeters, which is 0.5. So it's 8 divided by this product over here, and that gets us our concentration as being 0.10126, so on. So this is what my calculator is saying to me. The rule in science is that we must round off to at least 2 decimal places. So I'm going to round off to 2 decimal places, so I'm going to get 10, and remember your unit, it will be moles per cubic decimeter. That is your unit for concentration. And remember, the reason why is because your formula for concentration, your basic formula, is moles at the top divided by cubic decimeters at the bottom. Moles per cubic decimeter. There we go. We can see it in our units over there. So you'll get a mark. It's 3 marks. You get a mark for your formula, for substituting correctly, and for your answer with units. Let's do another question. Now, 5.3 is something that you're taught in grade 10, you tested on again in grade 11, and sometimes even in grade 12. They say there's a 10-gram sample of a compound, and they tell me it contains 2,66 grams of potassium, which is our element K, 3,54 grams of chromium, that is Cr, and 3,81 grams of oxygen, O. They want me to define the term empirical formula. I hope this is ringing some bells. So empirical formula is the simplest whole number ratio of atoms within a compound. Let me write that for you. If you need a recap on empirical formula versus molecular formula, click the links in my description below, but there's the definition. Let's work out the empirical formula of this compound. The first thing that I want you to notice is that they do tell me all the elements that can be found in this compound. So they tell me potassium, we mentioned that is K, they mention chromium, that is Cr, and they mention oxygen, which is O. If you add up the mass in grams of these compounds, you do get 10,01, and they do say they are taking a 10-gram sample of the compound. Now, our rule with empirical formula is sometimes we start with percentage composition, sometimes we start with mass. If we start with percentage composition, we assume 100 grams of the sample. And whatever that grams is that we start with, so here we're just starting with grams straight up. That grams we're going to convert to moles. So step 1 always is convert each of the grams of each of the elements into moles. So we're going to write our formula. Because we're working with grams, we use this formula. We're going to convert into moles for our individual elements. We're going to do potassium. We're going to do chromium. And we're going to do oxygen. So let's do it. I just need this formula written once on your page. So we don't have to rewrite the formula each time when we calculate the moles. We need to write it once. Let's calculate the moles of potassium. Now the mass of potassium is given as 2,66 grams. So that goes in the place of baby M, which is mass, 2,66 grams. We're going to divide that by the molar mass of potassium, which is basically the atomic mass number of potassium. So I hope you can remember that the atomic mass number, if we look at our periodic table, it is represented by the big number. So for potassium, it is 39. So going back over here, we say 2,66, that's my mass, divided by 39, and we get our answer. It's important not to round off at this stage. So what I've done is I've kept my answer to 6 decimal places, just don't round off. Then we're going to do it again for chromium. But remember, we're working at moles, we don't have to rewrite this formula again. But we're going to take the mass of chromium, which they tell me is 3,54 grams, 3,54, and we're going to divide that by the molar mass of chromium. Again, if you look at the periodic table, you should be able to find the molar mass of chromium. It's the big number, it's 52. So we're going to divide it by our molar mass, which is our atomic mass number, which is 52. And I get 0,0680,769. Just don't round off. This is a very similar answer to that one, which later on you'll see what happens because they are so similar. Then we're going to do oxygen. Oxygen, they say 3,81 grams of oxygen. So it's 3,81 is your baby mass at the top in grams, divided by molar mass, which is our atomic mass number. And if you look at oxygen, the atomic mass number, as you can see over here, the big number is 16. So we're going to say divided by 16. And let's work that out quickly. And there you have your oxygen in moles. Now what you're going to do is you need to write these as a ratio, and we need to divide all parts of the ratio. So in other words, all 3 numbers by the smallest number. So let's first write it as a ratio. We've got 0,068205 in a ratio with 0,0680,769 in a ratio with 0,238125. And effectively what we're trying to do is we're trying to find the whole number ratio, the simplest whole number ratio of these atoms. So we put them in a ratio, and in order to get them into whole numbers, we're going to divide all of them by the smallest number. This is one way to do this. So what we will be dividing each of them by, so we're going to divide them all by the smallest, and this is just the easiest way to do it. and we're going to divide it by 0,0680. This one over here, this middle one, is the smallest. So we're going to divide all of them by 0,0680,769. You can indicate the step. So what you can do is you can show me as a little fraction that we're dividing each of them by the exact same number. And then we're going to get an answer. So divided each of them by the exact same thing. As you can see, even the last one, I'm dividing all of them by the smallest one, the exact same thing. And when I do that, my outcome, and if you do this on your calculator with me, you'll see that for the first fraction, we get 1,001. Now, 1,001, that is very, very close to 1, and it's close enough for us to round down to 1. The middle fraction, we're dividing 0,068 by itself. So that's definitely going to get us 1. And for the last fraction, the 0,23 number divided by the 0,06 number, we get 3,49. Now we run into a little bit of an issue. 3,4978 and so on. That's what I get on my calculator. That is not close enough to 3 to round down to 3. It's not close enough to 4 to round up to 4. So if you look at our first fraction, when we divided our number of moles by the smallest number, so we take all our number of moles, put it in a ratio, divided by the smallest. After doing that, for the first one, we got 1,001. It's very close to 1. So that we could have rounded off. However, because for the third fraction, the last fraction over here, we get 3,4978. We can't round that off. Remember, this needs to be a whole number ratio. The only way to convert this into a whole number ratio is to think that 3,4978 is basically 3,5, 3.5. One way to get rid of a half is to multiply by 2, the reciprocal. Okay, so if we want to get rid of a 0.5, a half, a 0,5, we need to multiply by 2. Think about it. If you multiply 0,5 by 2, you get rid of it. You make it a whole number. You make it 1. If you multiply 2,5 by 2, you make it a whole number. You make it 5. So what I'm going to have to do is I'm going to have to multiply this one over here by 2 to get rid of the decimal. But because I'm multiplying this third fraction, this 3,4978 by 2, I have to multiply all of these numbers here by 2. Let's do it. So because I'm multiplying 3,4978 by 2, that ultimately is going to, I kept that long number on my calculator, I'm pressing times 2, and I'm getting 6,995. Now, grade 10s, 11s, and 12s, because that is extremely close to 7, I can round that up to 7. Now that I've gotten rid of that 0.5 or that 0.49 decimal, I can round 6.995. I can delete that and I can make that 7. So there we go. We've got our first whole number, 7. However, because I've multiplied this one by 2, so the third part of our ratio by 2, I have to multiply all the parts of the ratio by the same number. So what you do to the one part, you have to do to all the parts. So 1 times 2 is going to be 2. And then 1,001 times 2 is going to basically be 2,002. But again, that 2,00, that's close enough to 2 for me to round it to 2. So now we've essentially got our simplest whole number ratio of atoms. And if you look carefully, this first part of the ratio corresponds to K. So we've got 2 potassiums in this compound. The second part of the ratio corresponds to chromium. We've got 2 chromium atoms. And the third part corresponds to oxygen. We've got 7 oxygen atoms. And that means that our empirical formula, so we're going to say, therefore, our empirical formula is K2Cr2O7. Now in this question, we have an entire balanced chemical reaction and a chemical equation that goes with that reaction. And they give us information about one of the reactants. So they tell us how much sodium carbonate we are starting with in our reaction, 1,5 grams, and we add it to hydrochloric acid. And then they tell us about the product that is being produced. They say that a volume of 306 cubic centimeters of carbon dioxide gas was formed and collected under standard temperature and room pressure, and they give us the molar volume for that. First, they want us to balance the equation, which is an absolute basic standard thing that we always have to do when we do stoichiometry. So even if they didn't ask us to balance the equation, we know that before we do any stoichiometric calculations, so you see the 7 mark one over here, before we can even attempt that, we need to balance the equation. So we'll do that in a second, but I just want to show you the question. They want us to calculate the mass of sodium carbonate that reacted. Now you might be thinking, but they told us the mass of sodium carbonate. It says 1,5 grams of sodium carbonate. Now, what you need to understand is that mass, the 1,5 grams of sodium carbonate, that is what we started with at the beginning of our chemical reaction. It does not mean that the entire 1,5 grams of sodium carbonate will react. Okay? This is most likely what we call the excess reagent. Basically what that means is that not all of it will react in the chemical reaction, and there will be some left over. So what the question is asking is how much actually reacted. In order to know how much actually reacted, we need to work backwards. So we need to take the product that they give us, which is carbon dioxide, and we need to convert that to moles. Once I know the moles of the product that was formed, what was actually created, what was actually formed, the moles of that product, we use a mole ratio to work backwards to get the moles of sodium carbonate that was reacted, and therefore we can calculate the mass that was reacted. We will see that it's not 1.5 grams. Let's do this. Firstly, let's balance this chemical equation. If we take a look at our chemical equation, we can see that it is unbalanced. If it helps you to do this, then what I would recommend is draw a dividing line where the arrow of the reaction is and list out all the elements in our compound. So we've got sodium on each side, we've got carbon on each side, we've got oxygen on each side, hydrogen and chlorine. This may or may not help you. Maybe it can help you see what you need to do, what you need to multiply by. I don't need to use this when I balance, and as you practice, you won't need to use it either, but maybe in the beginning it helps you. So you can see on the left-hand side, you have 2 atoms of sodium, 1 atom of sodium on the right-hand side. Carbon, we have 1 on the left-hand side, 1 on the right-hand side. Oxygen, we have 3 on the left-hand side, 3 as well on the right-hand side. There's an extra 1 over there, plus these 2, that's 3. Hydrogen, we have 1 on the left-hand side and we have 2 on the right-hand side. Chlorine, we have 1 on the left-hand side, 1 on the right-hand side. Now, the first thing that's jumping out to me is the fact that I have 2 sodiums over here, but only 1 sodium on this side. So I'm going to put a big 2 in front of NaCl. Remember, we only change the big numbers. So basically, I've multiplied my sodium by 2, which has fixed the sodiums. I've also multiplied my chlorines by 2. And now my chlorines are unbalanced. So we have 2 sodiums on either side, which is fine. But now I have 2 chlorines on the right-hand side and only 1 on the left-hand side, which means I need to multiply this by 2 as well. In other words, I need to put a big 2 in front of the HCl. But by doing that, I also multiply the hydrogens by 2 on the left-hand side, which is actually perfect because I have 2 hydrogens on the right-hand side. So now what I've done is I've balanced all my elements. So as I mentioned, if it helps you to list out the elements like this in the numbers and see where you need to make adjustments, you can do it. After a while, you'll get the hang of it and you won't need to anymore. So basically now we've balanced the equation by putting a 2 in front of hydrochloric acid and a 2 in front of sodium chloride. Now, let's jump into the 7-mark question, but let's re-evaluate what the question is actually looking for. So they say calculate the mass of sodium carbonate that reacted. The mass of sodium carbonate that reacted. First of all, this is sodium carbonate. So I'm looking for the mass that reacted. So I'm going to write M over here and I'm going to put a question mark, and I know that that refers to the mass that reacted. Now remember, we actually started with 1,5 grams of sodium carbonate. So you might be thinking, but ma'am, why are we working out the mass of sodium carbonate that reacted if we literally know that the mass is 1,5 grams? Remember, I mentioned that this 1,5 grams is not necessarily the amount of sodium carbonate that actually is used up or that is actually reacted. This is the sodium carbonate that we start with. Now, a very, very big tip and something that is always true is in order to work out the mass that reacted, or the moles that reacted rather. In order to work out the moles of a reactant that reacted, or the moles that was used up, we can work backwards from our products. So if I know the moles of the product that was formed, I can use that in a mole ratio with the reactant to work out the moles of the reactant that was used up. So what that means is, as long as I know my products, so as long as I know the moles of my product, I work backwards in a mole ratio to work out the moles of my reactant. And that moles will be the moles that was actually used up. And you should know that once you have moles, you can convert it to mass. So this is our game plan. First step is to work with the products, work with the information about the products, and convert it to moles. So we're going to convert our information about our products to moles of products, which is CO2. Once we've got the moles of our product, we're going to use a mole ratio. So it's working backwards. So step 2 is use a mole ratio. The things that we put in a mole ratio will be CO2, because that's our product, as well as sodium carbonate, because that's the thing we're looking for information about. That will give us the moles of sodium carbonate that was actually used up. So the mole ratio, if you're working with a product, that will always give you the actual amount that we use in that reaction. And then we convert it to mass. So there's our steps, working backwards from our product, work out the moles of the products, and look at the formula that I'm going to be using. Number of moles is equal to volume divided by molar volume. The reason why I've chosen that formula when working with the product, carbon dioxide, is because carbon dioxide is a gas. They give me the volume of the gas in cubic centimeters. I will convert that to cubic decimeters, but that's volume. They also tell me to take the molar volume at room temperature as 24,45 cubic decimeters. So they're giving me molar volume. So I have enough information to work out the moles of CO2. Then I'll use a mole ratio, and my mole ratio will have CO2 in the mole ratio along with sodium carbonate. Now, why am I choosing those two things in my mole ratio? Because I've worked out the moles of my product and I want to jump across the reaction to work out the moles of sodium carbonate. Why do I want to work out the moles of sodium carbonate? Because I want the mass of the sodium carbonate that actually reacted. And we can convert those moles that we get from the mole ratio to mass using N is equal to baby M over big M. So let's carry out these steps. Now what I've done is I've converted my volume of carbon dioxide gas that was collected, that is the volume that was formed or produced at room temperature. So that was given as 306 cubic centimeters. I converted it to cubic decimeters by dividing by 1,000. The reason why I did this is because my molar volume, the unit is in cubic decimeters. And they gave me my molar volume. Now just remember, if they said that this reaction happens at standard temperature and pressure, then your molar volume will be 22,4. I know it is standard pressure, but this did not take place at standard temperature. Remember, standard temperature is 0 degrees Celsius. This took place at room temperature. So therefore, my molar volume is not 22,4. They gave me my molar volume. Now to work out moles, I use this formula. Number of moles is equal to volume divided by molar volume. You sub in your volume, which is 0,306. Don't round that off yet. Divided by 24,45. And there's my number of moles of carbon dioxide gas that was produced in this reaction. Once we know the number of moles of product that was produced, we can go backwards and work out the moles of the reactants, which is the things on the left-hand side of the arrow, that was reacted or used up. So the moles of our product, when I put that in a mole ratio with one of the reactants, that can always get us the number of moles of reactant that was used up. And that is step 2. So let's look at step 2. Step 2 says use mole ratio to work out the moles of the reactant that reacted. So because I'm going from carbon dioxide in my reaction and I want to go all the way to sodium carbonate, in order to jump from compound to compound in a reaction, we need to use the mole ratio, and inside the mole ratio goes moles. So we're going sodium carbonate to carbon dioxide. Those are the two things that are going to go in my mole ratio. Again, those are the two things. Because I worked out the moles of carbon dioxide, I now want the moles of sodium carbonate. That's a 1-to-1 ratio. Now, how do I know it's a 1-to-1 ratio? We look at the big numbers in front of the balanced equation. So there's no number here, so we assume it's a 1 mole of carbon dioxide, 1 mole of sodium carbonate. So it's a 1-to-1 ratio. And what that means is that if I produced remember our answer for moles was 0,012515 moles of carbon dioxide. It means that I used up exactly the same number of moles of sodium carbonate. Why exactly the same number of moles? Because it's a 1-to-1 ratio. So therefore, I reacted. Remember, the wording is you reacted or you used up 0,012515 moles of sodium carbonate, Na2CO3. But remember, the question doesn't want to know the moles of sodium carbonate that reacted. It wants the mass of sodium carbonate reacted. So our third and final step is to convert these moles of sodium carbonate that we got from the mole ratio back into mass. And we do that using the following formula. Number of moles is equal to mass divided by molar mass. Now, my number of moles is what we just got from the mole ratio. So that'll be 0,01215. You can also use a fraction. And then my mass is what I'm looking for. And my molar mass, remember, it's the molar mass of sodium carbonate. So you work that out using your periodic table. And you get 106 grams per mole. So that goes in the place of big M. It's your molar mass, 106. And then to get your mass, you say 0,012515, so your number of moles times your molar mass. And what you get for the mass that reacted was 1,32659 grams. And you may round that off to 2 decimal places, so 1,33 grams. Now remember, the question said we started off with 1,5 grams, but we only used up 1,33 grams. And we figured that out from working backwards from our products, and that's how we do it. Now, the question could have taken it a step further, and they could have asked you for the unreacted mass. And all you would do is you would take the mass that you started with, so 1,5, and you would subtract the mass that reacted. And the difference would be the mass that did not react. So 1,33 grams is the mass that reacted.